Give him a big round of applause, Professor Lewin. Thank you.
Thank you very much. The wonders of electricity and magnetism. What is electricity and what is magnetism? That's a very easy question to ask, but it is not possible to answer it, not in 2 lectures, not even in my 35 lectures, which I spent with freshmen on this topic. We do all know about electricity. Without it, no TV, no radio, no computers, no cell phones, no GPS, no light bulbs, no trains, no cars, no airplanes. Not even water, because water is being pumped up by electric motors. No gas. My gas at home ignites with electricity. I could not hear without electricity. I could not see without electricity, and my heart could not beat without electricity. In fact, none of us could think without electricity. Now, I realize there are some among us, perhaps, who even with electricity have different thinking. Life cannot exist without electricity. How about magnets? We have them on our refrigerators. You know them from compasses. And you can ask yourself the question, could we do without magnetism? And the answer is no. Electricity and magnetism are inseparable. One cannot exist without the other, and the other cannot exist without the one. This is one of the greatest discoveries ever made in the history of science. And I will talk about it later, and I will demonstrate that. That discovery was made in the 19th century. About 2,500 years ago, the Greeks discovered when you rub amber with a cloth, that it attracts pieces of dry leaves. And the Greek word for amber is electron, so you understand where the word electricity comes from. And then later in the 16th century, it was discovered that glass and sulfur have similar properties. In the 18th century, it was discovered that there are really 2 types of electricity. One, let's call it A, which we really all call now positive, and the other would be called B, which really we would call now negative. If you take glass and you rub that with silk, you get A. If you take rubber and you rub that with fur, you get B. And if you take amber and you rub that with wool, you also get B. A repels A, B repels B, A attracts B. Without any knowledge of electrons and protons, which we do have now, Benjamin Franklin in the 18th century suggested that all substances have a certain amount of electric fluid. He called that electric fire. And if you add fire to something, then it becomes what he called positive. If you take fire out, it becomes negative. So an excess of fire means positive, a deficiency of fire means negative. But he went one step further. He said, when you take this fluid from one and you transfer it to the other, then the other becomes positive, but since you have taken it away from the first one will then become negative. And that's a brilliant thought, because that is underlying the conservation of charge. You cannot create positive charge or negative charge. If you create positive charge one way or another, you automatically create the same amount of negative charge. And that's known in physics as the conservation of charge. Benjamin Franklin said, the more fire you add, the stronger are the forces between the objects. So if you have two objects and you add to both of them a lot of fire, both positive, they will repel each other. The more fire you add, the stronger will be the repelling force. And if one is positive and the other is negative, the more fire you add to one, the more fire you take from the other, the stronger will be the attractive force. He also noticed that the closer the objects were to each other, the stronger these forces were. Some of the substances that we know can conduct the fire. We call those conductors. All metals conduct the fire. All metals are conductors. But there are some that cannot do that, and we call those insulators. Good examples of insulators are glass, porcelain, and rubber. I have here a glass rod, and when I rub this glass rod with silk, I add fire. I create what we call nowadays positive charge. And here, on the left side, we have a balloon which is filled with helium, and the surface of that balloon is metal, so it is a conducting surface. If I rub this, I make the glass positively charged, I add fire, and I'm going to try to bring some of that fire on that balloon. So I'm going to touch this balloon to see whether I can transfer some of that fire. I'll do a little bit more. I'll add it to the other side. I'll do a little more. Okay, let's hope now that I have made that balloon, as we would say in modern language, positive. The rod is also positive. So if I bring the rod to the balloon, they should repel each other. And they do. But now, if I take the rubber, which I rub with fur, then the rubber becomes negative. And if I'm fast, so that there's still positive charge on that balloon, then the two will attract each other. But I have to be fast because charge may be leaking off there. The reason why it's so cold in this room is because we had the air conditioning on all night, because if you have moisture in the air, then charges leak off very easily. So now comes a negative rod, and it is attracting. So you have seen now that plus repels plus, plus attracts minus. I go back to my glass rod. Remember what Franklin said. If you make the glass rod positive, I hope that's still positive, by the way, then at the same time I must make this negative because charge is conserved. Let's see whether there's still positive charge on there. Yes, there is. Let's see whether this is negative now. Yes, there is. So you've seen that when I made this positive, that this one became automatically negative. When I comb my hair, I charge my hair and I charge the comb. Depends on the material. This is hard rubber, works very well. I would like to know whether the comb becomes negative and my hair positive, or whether my hair becomes negative and the comb positive. That's easy to test now. If that balloon is still positive, we shouldn't wait too long, but if it is, and if I comb my hair, and if the balloon is attracted by my comb, then my comb is negative. If it's repelled, then my comb is positive. And it's attracted, so my comb is negative. So we already know that my hair is now positive. I have here 2 bar magnets. And I'll make a drawing on the blackboard. Here is one magnet. A magnet has a north pole and a south pole. I have another magnet, the other one. It has a north pole and it has a south pole. The north and the south pole attract each other. The south and the south pole repel each other. The north and the north pole repel each other. So you will say exactly the same as electricity. Wrong. I now take a piece of plastic, and I can do that, and I make this side of the plastic negative, and I can make this side of the plastic positive. Plastic is very good insulator, so I can do that. I have another one. This side negative, this side positive. And indeed, the negative will attract the positive. The negative will repel the negative, and the positive will repel the positive. But now comes the big difference. If I cut this in half, this piece of the plastic is negative. And this piece of the plastic is positive. If I take this magnet and I cut it in half, then this is not north and this is not south, but this is north and this is south and this is north and this is south. And it makes me angry because I really would like north and south, more north in my left hand and south in my right hand, just as I can do here. So I cut it again. The same thing will happen. No matter how small I make it, always have north and south simultaneously. So it's very different from electricity. We therefore call magnets dipoles. Di means two, as you know. Electric charges we call monopoles. They can exist on their own. No north pole from magnetic field can exist alone, and no south pole. But there are physicists who are trying to find what we call a magnetic monopole. Many very brilliant physicists are trying that. And they know if they succeed, that they will get the Nobel Prize. Maybe it's one of you. So we now know something, of course, that Benjamin Franklin didn't know. We know that an atom consists of a nucleus, and the nucleus consists of protons, which are positively charged, and neutrons, which have no charge. Atoms have electrons, and they are negatively charged. I'll give you an example. Suppose we take a hydrogen atom, has one proton, and it has one electron. The magnitude of the plus charge and the magnitude of the minus charge are exactly the same, so they cancel each other, and so the atom as a whole is electrically neutral. It has neither a positive nor a negative charge. I take helium. It has two protons. It has two neutrons, but they have no charge. And it has two electrons. And again, the two negative charges and the two positive charges make the atom neutral. The mass of the proton, and also the mass of the neutron, is about 2,000 times larger than the mass of an electron. And in conductors, metals, I mentioned earlier, are conductors, electrons can move freely in conductors. So they can leave the atom, they can leave their proton, and they can move freely all by themselves. Protons cannot do that. So if I have an electric current going through a copper wire, then it's the electrons that move. They can move, the protons cannot. Now, I go back to my balloons. Now I have a balloon which is neutral. It's very easy to make this balloon neutral. This balloon is a conductor. If I kiss that balloon, whatever charge there is will flow through me to the earth and it's gone. Because electrons are free to move, nothing is stuck, so it's very easy for me to make this balloon neutral. Whatever charge there was, believe me, it's gone. So now I have this neutral balloon. It's a conducting balloon. And here I come again with my glass rod, positive. Electrons are free to move in a metal. The surface of that balloon is metal. So the electrons who are being attracted by the positive charge would like to go to this side of the balloon, and therefore the other side has no choice, becomes positive. And since the negative charge here is closer to the positive charge than the positive charge to the rod, the attractive force here is larger than the repelling force here. And that means that if I approach with my glass rod and I charge the glass rod positive, even though that balloon is neutral, when I approach it, it should come to my rod. That phenomenon, very important in physics, has a name. It's called induction. So the balloon remains neutral all the time. And it's coming to me, as I predicted. I can do the same thing with a negative rod. If I make this rod negative, well, then this side will become negative and this side will be positive. So it should also come to a rod if I make the rod negative. Again, induction. Let's see whether that would work. So again, through reasons, if the balloon is indeed still neutral, which it should, it didn't touch the rod. Sometimes that happens when you're in an experiment, it goes to the rod and it touches it. Well, then it's no longer neutral, of course. But if it's still neutral, then for the same reason that the balloon goes to the positively charged glass, it should also come to my rubber one. You see it does? Very clearly. So it's again attracted. Induction. Now comes something very tricky. I have here a balloon which is not a conductor. We think it is neutral. Am I 100% sure? 99% sure. It's been sitting there for more than an hour. We never touched it. We never rubbed it with anything. So we assume that that is a neutral balloon, which is now an insulator. So here is this balloon, and it is an insulator. So electrons cannot freely flow if I bring here my glass, which is rubbed, positive charge. Electrons cannot flow to this side, which happened here. And so you would think there is no reason for this balloon, which is an insulator, to go to the positive side. But now there is something else which happens, which is even more subtle, which is also called induction. The atoms in the surface of this balloon become a little bit oblate, and the electrons spend a little bit more time on this side than they did before. And so here is then the nucleus. This is some kind of polarization of charge. The electron cannot leave the atom. Remember, it's not a metal. It's stuck to the atom, stuck to its proton, but it spends a little bit more time in this direction. And if many of them do that, this side becomes negative, and so this side becomes positive, and therefore the balloon should be attracted by the rod. Let's see whether that works. If it comes to the rod, it may do it very violently if I'm very close to it, and it may actually touch the rod then. Well, there's nothing I can do about that. What counts is for me that it comes to the rod. But I may not be able to avoid a collision. Yeah. You see, at the last moment it decided to go in. I couldn't avoid it. That's also induction. It's exactly the same phenomenon. So you now understand why rubbed amber can attract dry leaves. Because if it can attract a neutral insulator, well, then induction would also work on leaves. So I hold amber, rubbed close to the leaves. The leaves become, through induction, they will be attracted by the amber. And that is something that I want to demonstrate now, not with dried leaves, not with amber, but again with my comb. I'm going to make it a little darker so that you can see this better. And if everything works, you should see it there. I have here small pieces of paper, so it's not leaves, but small pieces of paper, confetti. Can you see them? Yes, you can. So, this is what the Greek had for amber, and this was their leaves. So I'm combing my hair. We already know that my comb will become negative. And induction will pull those pieces of paper towards my comb. Now watch very carefully. You see them? But now comes my historic question. I always ask my students a question. You may have noticed, and if not, I will show it to you again, that many come to the comb and immediately are repelled. That's reasonable, because they become negatively charged when they touch the comb, because the comb is negatively charged. Induction brings them to it, they become negatively charged, and so they immediately repel each other. But some stay stuck on the comb. And I want you to explain that. That's your homework. I'll show it again. That some of them are not repelled immediately, but stay on the comb. I see some go back and forth, but many now stay on the cone. And you are going to explain that. I've here neutral balloon, insulator, it's not charged. If I rub that, I can charge it. And it loves to be rubbed by nylon or by polyester. That charges it very nicely. I could have tried it on my cotton shirt, but this is going to work much better. Believe me, I've done this for 46 years, I know. So here's the balloon, and I'm going to rub it. I'm charging it now on this side because it is an insulator, so no charge is there. The charge will only be here, but I rub it. I don't recall whether the balloon becomes negative and I positive or the other way around. I don't remember. That's irrelevant, but it becomes charged. And now it's stuck. If you can explain why these pieces of paper get stuck on the cone, you can also explain that. I have one more. Oh. Also a nice one. It's stuck. Teeny weeny little balloon. Aren't they cute? It's easy to charge them. You want to see something? Same as that. Amy, would you mind having one like this in your hair? I can tell you would. Come over. You were very beautiful, but now, even more beautiful. But before you go back to David, there's another one here. So now you can go back. Thank you, Amy. Now we are going to do an experiment for which I may end up in jail. I'm going to tell you, I want to volunteer. Yeah, you look great. But before you volunteer, yeah, come on. What's your name?
Nelson.
What?
Nelson.
Nelson. Nelson, I'm going to beat you.
Okay.
It's a sacrifice for the sake of science.
Sure. Okay.
You ready for that?
Yeah.
Okay. If you come with me, and I would like you to sit down on a special stool that we have, which is very well insulated. But before you do that, you get the magic jacket. Yeah, great. Terrific. Now, use this chair. Be very careful. The last thing I want you to fall. And sit on it. And your shoes should not touch the table. Excellent. Nelson, I'm going to beat you with fur. But I'm going to stand on this very thick plate of plastic. And so when I beat you with fur, you will get charged, but so will I. If you become positive, I become negative. Your charge cannot flow away because you're well insulated there. Mine cannot flow away either because of this thick plate. And I want the audience to see that as I keep beating you more and more, that indeed you will become charged. I have here what we call tinsels. You use them Christmas in your Christmas tea. So these are these very thin pieces of aluminum. You're going to hold that in your hand, and I will hold one in my hand. If your body becomes charged, you better believe it, your hand will become charged, the tinsels will become charged, and so these tinsels, which are charged, will repel each other, and so they will do this. They will spread out. That is the sign then that you're being charged. And I can make a pretty good estimate. The estimate will probably be, I would modestly get you up to maybe 30,000 volts or something like that. I too will have mine to convince you that indeed I am also insulated just as you are, and so my tinsels should also start spreading. So are you ready?
Mm-hmm.
Are you happy?
Yes.
Are you nervous?
Not really.
You should be.
That matters.
Okay. There we go. Hey, look at your tinsels. You see that? Mm-hmm. They're spreading. Mine should do the same. Oh, one of my feet was on the table. That's not good. Oh, boy, yours are fantastic. Yeah, mine can also, they also start spreading. I would estimate now easily 30,000 volts. And what I'm going to do is, look at me. I'm going to touch your nose.
Okay.
Did you feel the electric shock?
Yes.
30,000 volts.
Yes.
This is only the beginning. We have a neon flash tube, which Bill is going to give me. The neon flash tube will give light. Thousands of volts are necessary for it to give light. You're going to hold this end in your hand. You can still keep the... Okay. Don't let go. It's a very expensive tube and we only have one of them.
Okay.
No, seriously, don't let go. I'm going to beat you again. And we will see that your tinsel will work again, and my tinsel will work again. And then, instead of touching your nose, that means a current will flow between us that gave us the shock. I felt the same shock, of course.
Yes.
Now, I will touch this end of the tube. That means the current will go through the tube. Several thousand volts, the tube will be happy, and the tube will give a flash of light. And we do that in darkness.
Okay.
Yeah? All right, there we go again. Boy, you have super tinsels. It's because you wear that magic jacket. Ah, but mine are doing okay too. But yours are super. Boy, I think we're way over 30. Oh, look at that! Way over 30,000 volts now. Bill, can you put the light on dim first? Okay, and then I will ask you very shortly. Okay, make it dark, Bill. And now I'm touching the tube. So you've seen current. Applauding for you. They are applauding for you. Now be very careful when you get off here, because we don't want accidents. Be very careful. Thanks, Bill.
You want your jacket back?
It would be nice to get it back, yeah. It's one of my favorite jackets, actually. Thank you, Nelson. Let's talk about magnetism. Already some 2,500 years ago, the Greek discovered that some rocks attract iron. And they found them in the district of Magnesia. These rocks contain iron oxide, and we call them nowadays magnetite. Let me move this away. Perhaps, Bill, you can put it in front of the desk so that it decorates the room, but no obstructions. In 1100 AD, the Chinese used these needles of magnetite to make compasses. And in the 13th century, it was discovered that magnetites have two places of maximum attraction. In other words, it was recognized, in principle, we call it now, that there was a South Pole and a North Pole. That's where the ends, where the forces will be maximum. So each piece had two poles. In the 16th century, Gilbert discovered that the Earth itself is a magnet. So he explored a large fraction of the Earth, and he used these magnetite needles, the compass, this be the north side, and this the south side, which could spin freely, either on water or on a pin. And then he noticed that this was always pointing somewhere north. Maybe not exactly our geographic North Pole, but very close to that. Nowadays, we call that the magnetic pole of the Earth. I bet you what you didn't know, that magnetic pole in North Canada is not the magnetic North Pole. It is the magnetic South Pole. Because north attracts south. Even though we always call it the magnetic North Pole, that is the wrong name. But who cares? It points towards the north. important discovery. In 1819, a crucial discovery was made by the Danish physicist Ørsted, historically of immense proportion. He demonstrated that the magnetic needle responds to an electric current. In other words, he made the connection between magnetism and electricity. And an explosion of research evolved in the 19th century. Names like Ampere, Faraday, Volta, Henry, you may have known, you may have heard about them. All this culminated in the brilliant work by the Scottish theoretician Maxwell. He composed what physicists nowadays would call a unified field theory. The unification was magnetism was unified with electricity. Originally, they were looked at as two different things. In this unified theory, it was clear that they really are one. They are intimately connected. One cannot exist without the other, and the other cannot exist without the one. And this was summarized by Maxwell in 4 equations, which we refer to as the 4 Maxwell's equations. Not all 4 he invented. He only worked on one of the 4, but we refer to them as the 4 Maxwell's equations. If I showed them to you, you would be so shocked you might even leave this room. So I will not show these 4 equations. But I spent 36 lectures at MIT for my freshmen, and it's all about these 4 equations. And once you have learned to see through those equations, you would agree that they have an intrinsic beauty that is unimaginable. It's so important that when we reach that point that all 4 equations are understood, I hand out flowers in the lecture hall. Every student gets a flower. 600 students, 600 flowers. Clearly, I want to show you this demonstration. It's historically so important. I'm going to show it to you. We have here, I'm going to put the light a little down. Okay. We have here a compass, and here is a copper wire, and the compass is pointing in the direction that it likes to point. I'm not suggesting that it is pointing towards the north, because this is MIT, and you can imagine how many magnets are floating all over the place here. So it's pointing in the direction that it likes to point, but that may not be the geomagnetic South Pole. I'm going to have a current going through this wire, for which I use a car battery. I'll first let the current go through it this way, and then I will reverse the current. So there we go. That's what Ørsted did. The current going through the wire, and the magnet, the compass, responds to it. points now in a different position. An unbelievable discovery. Changed the whole concept of physics in the 19th century. It connected electricity with magnetism. Now I will break the current and it will go back to its original position. And I will reverse the current. And now it rotates again, but 180 degrees different. In other words, it even sensed in which direction the current was flowing through the wire. I'll get the lights back on again, because I don't think we need darkness. I've never discussed with you that batteries have the ability to move charges through conductors. I will talk about that more next time. Think about it like that water pumps can pump water through a hose. A battery can pump charges through a conductor. Currents, electric currents, are moving charges. That's what an electric current is. It's all what it's about. Charges are moving. If currents can produce magnetic fields, which they did, the compass responded. A key question now is, can a moving magnet produce an electric current? And that question was answered by Faraday. Equally important, historically. He showed that indeed a moving magnet can produce a current. And I'm going to show you that demonstration. And the way we do that is we have a magnet, very strong magnet, looks a little bit like this, not exactly, you will see it shortly, but something like this. This is the North Pole and this is the South Pole, and so the magnetic field in here is very strong. It's right there. So strong that I bet you that that compass knows that. That's strong. And what I have here is copper wire, thousands of windings of copper wire. Thousands. The copper is insulated. On the copper is a very thin layer of insulator, so they don't make contact with each other electrically. And this is one end, and this is the other end. And we connect here a light bulb. And if I take this magnet and I move it very quickly in the direction of that coil, then I do exactly what Faraday did. Namely, you change the magnetic field, it causes a current in this coil, and the light bulb will give light. That's the proof that there was a current that you created by that changing magnetic field. Now, in our case, this is extremely heavy, so instead of moving the magnet to the coil, I'm going to move the coil to the magnet. That's just a little easier for me. This is very light, and the magnet is very heavy. So here you see that coil, thousands of windings, and this is that little light bulb at the end, as you see that there. I'm going to make it a little darker so that you can see the light better. So all I'm going to do is move this coil now through that opening. I'll first do it very slowly. Little bit of light, little bit of light, more light, more light. Faraday discovered the faster you move, the more light you get. I can get a tremendous amount of light. Did you see how fast I moved it? Oh, I moved it so fast that I blew the bulb. You may be disappointed now. We have some spares. Let's see. Yeah, it's still working. It's again working. So I'll pull it out quickly again. Did you see the light flash? Maybe it's broken again. We don't know. Let's try again. No, not yet. But you do want to see it broken again, don't you? Yeah, I know you. Let's give it a shot. Yeah, we managed. When Faraday made this discovery, he had an interview with a news reporter. And the news reporter said, "What is the use of it?" And Faraday answered, "Someday you will tax it." Faraday's law is one of four Maxwell's equations. Faraday's law runs our entire economy. Without Faraday's law, all we would have is candlelight, and the quality of our life would be 18th century quality. No TV, no cell phones, no video games, no GPS, no radio, no trains, no cars, no airplanes. Life would be unbearable. Faraday's law runs our entire economy. So how do we produce so much electric power to satisfy the world? Well, we move coils through magnets, or magnets through coils, which is done at power stations. Of course, you get no energy for free. So, we use coal, oil, nuclear energy, waterfalls, wind energy, solar energy. But in all cases, in almost all cases, you're moving magnets through coils. This is my emergency light. I have a house in Connecticut, and we often have power failures there. No light. This is a dynamo, and when I pump it, I move coils through magnetic fields. That's all I'm doing. Faraday's law in action. I have to do the work, of course. There's no such thing as a free lunch. But it works. So this brings me to the subject of power. What is power in physics? Power is energy per time unit. So power is energy per second. So joules per second. Joules is energy, so joules per second is power. We have a unit invented for this, for joules per second, and we call that unit watt. So 1 joules per second is 1 watt. Just easy to talk about when you buy a light bulb, to say, I want a light bulb of so many watts. Suppose you have an appliance which requires 100 watts. That means 100 joules per second to function properly. And suppose you run that appliance for 10 hours. Then the amount of energy that you have used is what we call 1 kilowatt hour. And we spell that as follows: 1 kilowatt hour. Watt itself is power. But this is energy. Because look, if I bring the second to this side, then 1 joule is 1 watt times the second. And so here you see K is 1,000, that is 10 times 100. Watt is the joule per second, and hours are the 3,600 seconds. If I do this, the electric company charges me about 25 cents. For every kilowatt hour you will see on your bill, you pay about 25 cents. Now I would like to test a very strong person in the audience to generate power. Who is willing to do that? To generate electric power, human power. Come on, you look strong enough. When you rotate this, and you can start rotating right now, I may make it a little darker. Yes, I will. You rotate it. You can rotate it in any direction, but this would be fine. Then you may be able to power this light bulb, which is 15 watts. Man, you are impressive. 15 watts. You getting tired? 15 watts is nothing, right? Hold it. This is too easy for you. You know what I will do? I have here 6 light bulbs. All 15 watts. 6 times 15, it's close enough to 100. So it's about 100 watts. Try it again. I don't blame you. Keep going. Keep going. Keep going. Come on, keep going. Hey, man. What is your name? What is your name?
Michael.
Michael. Michael, I'm going to make you an offer that you cannot refuse. If you do this for 10 hours, then the energy that you have produced is 1 kilowatt hours. 100 watts for 10 hours is 1 kilowatt hours. I would have to pay 25 cents to the company. I will offer you a whole dollar. Man, what a summer job. 10 hours and a whole dollar.
Wait, are we serious?
Am I ever not serious? Can you imagine that a company can do that for 25 cents? And why can they do that? because of the oil that we are using, because of the coal that we are using. But that is not going to last. Maybe nuclear energy is readily available, but that too has its problems. You remember 3 Mile Island? You remember Chernobyl? You remember Fukushima? We do have a major energy problem. And your muscles are not going to solve it, but your brains may. Thank you very much. See you next Friday.